Now let's take a look here at example number 9. We're going to try to repeat the process of what we've done in the last two videos and find two more derivative formulas, one for the inverse tangent function and one for the inverse cotangent. Now actually, I'm going to ask you to try to work through these on your own. And don't be too intimidated. These are actually easier than both of the derivations we had in the last two videos. So pause the video here and give these a shot. Can you start by taking that inverse tangent maybe, rewriting it into that other form, and then slowly trying to come across a derivative formula and then get it completely in terms of x. Go ahead, pause the video, give it a shot. Even if you can't fully figure it out, that's okay. You might still be able to test yourself and see what you've understood. And then after you've paused the video and tried it out, unpause and you'll see me work through each of the solutions. All right, well hopefully you actually did go through and try that. Here's how we could actually determine the derivatives for each of these. So I'll start by stating that if we have y is equal to the inverse tangent of x, then that means that the regular tangent of y will be equal to x, and I'll state where y is a specific type of angle. So where y is going to exist in the interval from negative pi over 2 to positive pi over 2, and this will be excluding the endpoints. So again, on my unit circle, I'm dealing with kind of this right half of the unit circle. Now, of course, once I have this, I can take the derivative implicitly. So I'll calculate the derivative of the tangent of y with respect to x on the left, and the derivative of x with respect to x on the other side. So this is going to get me the secant squared of y times dy dx, using my chain rule there, equals 1. This is going to give me that dy dx is going to be equal to 1 over my secant squared of y. And so again, I have a derivative formula here, but I'd like to get this in terms of x. And so to do this, you could note another trig identity. Remember, we had the identity that the tangent squared of y plus 1 was actually equal to the secant squared of y. So I can actually use this identity to replace what I have. So I can say dy dx is equal to 1 over the tangent squared of y plus 1. And so now this is an update, but I still want to get this all in terms of x, and so I need to get rid of this tangent of y. But you may have noticed that's pretty easy because we already said that the tangent of y is equal to x. So since I have tangent y squared, I'm going to have x squared, and I end up with this. So I end up with that the derivative of my inverse tangent function is actually just going to be 1 over x squared plus 1. Or, of course, you could rewrite the denominator in the other order and write 1 plus x squared. Now, in the same way, we can calculate if y is equal to the inverse cotangent, then that means that the cotangent of y is equal to x. And of course, this is going to be where I'm going to have my value of y existing in the following interval. So I'm going to have y existing from, I should have a parenthesis there, not a bracket. But y is going to be existing in the interval from 0 to pi. So again, that means that I'm going to be working here with like the top half of the unit circle. So I take my derivative implicitly here. So I'm going to do the derivative with respect to x of the cotangent, and the derivative with respect to x for the value x. This is going to get me the negative cosecant squared of y dy dx from my chain rule is equal to 1. And so that gives me that dy dx is equal to 1 over my negative cosecant squared of y. Now again, I can see that this here is a nice formula so far, but if I want to get it in terms of x, I can again note the identity. And this identity that I'm going to use this time is 1 plus the cotangent squared of y is equal to the cosecant squared of y. Now if I use this, I can state that now my derivative for my inverse cotangent function is actually going to look like 1 over, let's see, I'm going to end up with a cosecant squared of y, but if I replace 1 plus cotangent squared of y in there, I'm going to bring that negative just up to the top to keep it out of the way. And if I put 1 plus cotangent squared of y on the bottom, and then recognize that cotangent of y is the same thing as x, I can actually write this denominator as 1 plus x squared. And so you'll see here that I can very, very easily and quickly arrive at these two formulas for the derivatives of the inverse tangent and the inverse cotangent. And very interestingly, you'll notice that they're almost the same, right? I mean, it's just that the inverse cotangent derivative has a negative on it. So hopefully you were able to get to these answers. If not, hopefully this helped to explain a little bit of what was going on. And if you are looking for potentially even more detail, you can always take a look at the notes that are posted up in Blackboard.